Good morning. My name is Dan, and together with my colleagues Ian and Philippe, we will be discussing the project presented by Semiconductor, Bench Automation Design for the Estimation of Transient Thermal Resistance. Now, the ultimate motivation behind this project is we wanted to be able to estimate the transient thermal resistance of a field effect transistor or FET device. And what transient thermal resistance is the degrees Celsius change in the device per watt that it perceives. So the reason that this is important is thermal overstress is one of the most common failure modes experienced in the field. So of course, there's already a way to find out what this parameter is, but the current method that's employed at Semiconductor isn't necessarily an efficient one. The current test is a manual test that consists of a device under test or DUT attached to a measurement circuit, which is attached to various bench equipments. Now, the engineers currently have to adjust all these values by hand. They have to change the resistors out by hand. So our goal is to save the engineers time and cut down the testing time from 2 weeks down to just a single day. This will free up the engineers to work on other projects, interface with customers, as well as free up other bench equipment to be used for other projects. Now, the current test, we went there, observed it in order to get an understanding of what we were going to be fixing, and it's a rather inelegant test. You can see we have parts that are taped down, and we have the resistors actually hanging off the desks. So for the test, there's 12 different pulses that occur. So every time you want to send a different pulse, you have to change out the resistors. And we saw when that was happening, wires were coming loose, and it just wasn't an efficient test because you could end up running an entire pulse through, waiting for it to cool down, and realize that you hadn't had it hooked up correctly, and you just wasted a bunch of time. So we felt that our design should be something that you'd plug it in and just be able to walk away from it. So this kind of brings us what's to expect of our best anticipated outcome. So as I already mentioned, automation is a big concern. We want to bring it down from just 2 weeks to a single day. The current values for transient thermal resistance is actually already given to the engineers on Semiconductor, but they're based on purely theoretical values from a lab. So we wanted to have concrete values that they can give their customers, but our values have to be accurate enough that they'll either complement those theoretical values or bring reason to question them as being too conservative. The last aspect is modularity. So not all component packages are created equally. Some have multiple pins for VDD, some have multiple pins for VSS, some only have 8 pins, some have 16 pins. So it wouldn't make sense for us to design a whole new board every single time that you want to test a different component, so we ended up opting for a daughter card motherboard system.
So on behalf of the onsemi bench team, I'd like to proudly say that we have achieved the best anticipated outcome. We wanted to design a test set that was both robust and variable in order to test different kinds of devices. These devices fall into one of two different categories, smart FETs and discrete FETs, and each category has its own unique measurement circuit used to test the transient thermal resistance. Pictured here on the left is the smart FET circuit, and here on the right is the discrete FET circuit. We combine these two into one design, allowing the user to test both smart and discrete FETs. Pictured here is the PCB layout of our design. We implemented 12 push-pull circuits, and these circuits act as electronic switches. An onboard microcontroller, seen there, sends signals to and activates these switches, and this is what allows us to send different levels of power and also control the amount of time that the power is applied to the device for. Here is the PCB fully manufactured with all the components installed. You'll notice a lot of banana jacks around the board. This is where we actually install our power resistors, and the power resistors are what allow us to have a finer degree of control over the power that's applied to the device, which is seen here connected to the center of the board. Each device will have its own unique daughter card manufactured for it. These daughter cards are created with strict standards set by the Joint Electron Device Engineering Council. And we actually designed one using these standards for the NCV 84160. This is an Semiconductor smart FET, and this is actually the device that we used for our testing purposes. The purpose of these daughter cards is what allows us to easily remove, replace, and test different devices with relative ease.
Here is the system overview of the project. We have the computer connected to the power supply to power up the board and the microcontroller. It is also connected to the microcontroller to control the input pulse of the device, thermal stream for applying external heat, multimeter for getting the calibration voltage, and lastly the oscilloscope for getting the average power and the average forward voltage of the diode inside the device. And here's a demonstration of how our automation test works. The GUI starts with selecting a device name that has to be tested, and it asks for a delay input on the oscilloscope. Then it automatically opens an Excel file and creates 13 different sheets for the summary and the raw data of the measurements. Then it starts pausing the device at 100 microseconds. Right now it is measuring the average power and the average forward voltage. Then it stores the values to the Excel file and calculate the average power and average forward voltage at 100 microseconds. This is a 500 microsecond pulse, and in order to complete a full test, the device must be paused 12 times from 100 microseconds to 100 seconds. Overall, after doing a final automation test, we got a very close result, and here is a graph comparison of a SmartFET device that we tested. The graph on the left are the accepted values, and the graph on the right was generated from our automation test. And as you can see from our graph that we got a minimal error from the accepted values. So we are gladly to say that we met the best outcome of this project. And lastly, we would like to say shout-outs to our technical director, Kevin, for coming today and making this project possible. Thank you.